Hi, so welcome back. In this lecture, we will learn about second order linear ODEs, but with a new perspective. It's called the D operator method. So before I start the method, the D operator method is basically to find particular solutions of differential equations. However, the method is not, so today's lecture is going to be a slight digress from what we have been doing, which is solving linear differential equations. What D operator method does is it brings in another field of mathematics, which is the field of algebra. And there are certain properties and structures, algebraic structures, which are called rings and groups, which I will explain now. They have their own properties, they have their own general rules, which can be applied, or they can be used to at least view ordinary differential equations from that perspective as well. And some of those tools actually come in handy in solving linear differential equations. And so the reason I said that today's lecture is going to be a slight digress from what we have learned is because we will learn some of those properties and tools and structures which are very basic ideas in algebra. And the good thing is these basic ideas, they find applications in almost all branches of mathematics, because that's the beauty of of a general theory, which if any other field or any other aspect or problems really which start to follow in that framework, which are really the general rules and properties of a field. If a problem starts to follow those kind of properties, then you can apply the general rules that are already developed in the theory to solve those problems. Okay, so with that, of course, when you're solving a problem, you can look at it from different angles, different perspectives, and this is just one of those examples where we will bring in a new perspective to solve differential equations, or to find particular solutions of differential equations. So the method will be D operator. Now, the first thing I'll do is to not talk about differential equations at all, but to talk about certain algebraic structures, okay? And then I will bring in the differential equations slightly, just to tell you how things fit in here. So, all right, so let's just start. The thing is, if you have a set, and I'm going to call that set G. So first thing we will define is what is called a group. That's a very basic structure that you can give to any set. If you have a set along with some operation, which is normally called the binary operation. I'm writing it as plus here, but this plus does not really mean the plus that we already know, that is the addition symbol in real numbers. The addition symbol here is a general symbol that depicts an operation. For example, if you look at ordinary addition, which is the addition of real numbers, it is an operation between two numbers. For example, 2 plus 3 would be 5. But similarly, so I'll just give the example here. 2 plus 3 is 5, obviously. But this plus is the addition on real numbers 2 and 3. If you have two matrices, for example, I have the matrix 1, 1, 1, 1, and I have the matrix 2, 2, 2, 2, I can also use the plus sign here. They are not the same plus sign, but as symbols they are the same. Here the plus sign means really you have to add them component-wise. So this really becomes 3, 3, 3, 3. Okay. This plus sign is a plus sign that is operating on two matrices, which are not elements of real numbers. They are made up of real numbers, but it has a different structure on its own. These are arrays. Okay. So we may be using the same symbol But it's a very general thing that even though we use the same symbol, they don't really mean the same thing, because they are applied to different things. Complex numbers, a plus ib plus c plus id, okay. I mean, I'm using plus here, but that's just, let's say that's internal to the structure. But this plus really means that you add the real parts, a plus c, and then you add the imaginary parts, b plus d, okay. And this plus here, this plus again here is really, it's like, it's like a bridge, or not even a bridge. It's like a conjunction. Okay, you can choose to write a plus ib, or you can choose to write ab in coordinates. They mean the same thing. If you know that the first element here is the real number, the second element here is the imaginary number. Okay, it doesn't matter how you write it, whether you write it in this form or you write it in this form. The plus here is really a symbol just to tell you that there are two numbers here, okay? So I'm not worried about this plus. It just means you can replace it by a comma. But what I mean by this plus here is that it's not the same plus as real numbers where you just add them and you get a 5. No, this plus means that you add them component wise, a to b and c to d, okay? A to C, A with C, and B with D. Yeah. So, as these examples would bring out, that even though we are using the plus sign everywhere, they don't mean the same thing. They have different functions on different sets that they're acting on, okay, or that they are binary operations on. So, when I write this plus, I mean whatever this plus may be defined as on a general set G, okay? So if I give you a set and I call it, and I give you a structure on it, and I give you an operation on it which I call plus, don't bring in your bias and think that it is the same plus as we use for real numbers. It's just a symbol, and we can define the plus, the addition sign here, the way we want to, that is apt for this particular set, okay? So when I write, let's come back to what is a group, therefore. So if you have a set and an operation on it, plus, which really is a binary operation because it acts on two things, like 2 plus 3, this plus this, it will be called, this tuple, this pair together will be called a group if it follows 4 conditions, okay? These 1, 2, 3, 4, not the 5th condition. The 5th one has it's an added condition, okay? So the first condition that it must follow is that there has to be closure. In other words, the operation must be closed. So what I mean by that is, if you take two numbers from G, or two elements, I can't call them numbers. Numbers means real numbers. So if you take two elements from G and you add them in the sense of G, okay? Not add them like real numbers. If you add them, then you must get to this new element must be an element of G. For example, if you added two matrices, you got a matrix. If you got something else, then this addition sign would not be closed, okay? So, the addition must be defined in a manner that it will be closed in G. In other words, take any two elements, add them, that must be an element of G. So then plus this addition sign would follow closure, the closure property. It should be associative. In other words, this property of associativity means that if you take 3 elements, then it doesn't matter in which order you add them. You can add the first 2 and then the C, or you can add the last 2, C and B first and then A. They should come out to be the same. So plus should be defined in a manner that this property also holds for any numbers A, B, C. There must be an element 0. which I will call the identity element, or more specifically, which will be called the additive identity, because we are using the plus signatures, a plus sign here. So, what is the additive identity? It means that if you have an element, forget how it looks like. It looks like a 0, but forget how it looks like. If you have an element, which I'm writing like this for the moment, writing like 0, such that if you add it to any element A from both left and right, and you still get A for any element or for all elements, then that special element would be called an identity. Okay? And we use the symbol 0 for the identity. Okay? Now, there may be a confusion, but if you can understand that, if you can get rid of your confusion for plus, you can get rid of your confusion for 0 also. 0 here doesn't mean the 0 of real numbers, because, of course, for real numbers, you would write 2 plus 0 is 2. That's fine. But what about matrices? For a matrix, I think if you have zeros everywhere, then you would get one, you'll be returned the same number, or same matrix, you will get 1, 1, 1, 1. So this whole matrix with all 0 entries is acting like the 0 element in the world of matrices. Okay, so I'm calling it the 0 matrix, and I'm giving it this name. I'm writing it like 0, but really it is not the same 0 as the real number 0. It is a 0 which has 4 real number zeros in it. Okay, so when I say 0, it's a 0 according to what this group is. When I say 0 for complex numbers, yes, you will write it as 0, but what it really means is 0 in the real place and 0 in the imaginary place. That's what, even though we call it 0, and we have called it 0 all our life, we don't mean it's actually 0. It means that there are 2 coordinates in the 0, and they're individually both zeros of the real numbers. Okay, so I hope that's clear. Then there will be an element, so that's the identity element. I will refer to it as the additive identity. Additive identity, because we will encounter what would be a multiplicative identity later. Now, if there is an element, or now come to the next one, which is the inverse property. Every element in G must have an inverse. In other words, for an element A, you must find another element. Forget how I'm writing it. I'm writing it as minus A. But again, this minus A is not exactly the minus we know from real numbers. But think about if you're given an element A and you can find another element which I'm writing as minus A, such that if you add it to the original element, you get the identity back. Then this element, this new element, is called the inverse. Actually, this should hold from both sides. So minus A should add from the left as well to give you 0. Okay. So if you can find such an element, then that element would be called the inverse. And since we're using addition, we would call it the additive inverse. Okay. So, and this should happen for all element. So if G and the plus sign so defined on it follows all these 4 properties, then this will be called, or this will be qualified as a group. Okay. Now it may have some additional property, which would be the property of commutativity or being an abelian group. In other words, if you take 2 elements, any 2 elements, and if you swap their positions in the addition, and still the answer remains the same, then, and if this happens for all elements A, B, and G, then G plus would be called, it's a group because it follows all 4, but it's a new kind of group. It's called an abelian group or a commutative group. Okay, so that's what it means to be a group. Okay, right. Now we come to what is called a ring. Now, ring would mean that you would have to add another structure to it, another operation on it, which is the multiplication operation. Again, I'm using the word multiplication as I have used addition before, but addition was not really only the real number addition. It meant what it would go with, how it could be defined on G. Similarly, I'm adding a new binary operation. So you have a set and you have the addition sign on it. So this three tuple, in other words, three things here together, would be called a ring if the first two, in other words, the set and the addition operation, is a commutative group. In other words, it follows all the 5 properties. Okay, if that is a commutative group, then it satisfies the first condition. So to be a ring, it should satisfy the first condition. It should be a commutative ring with respect to addition. The multiplication must be closed and associative. The two properties here, closure and associative, first two properties. So the multiplication, it doesn't have to follow all the properties. The multiplication has to just follow the closure property. That is, now if I, just like I had added the two elements and I got an element of G, I would multiply the two elements and I would get an element of R. If that happens for all AB, then I say that the multiplication is closed. Similarly, if I multiplied three elements of R in any order and still the answers were the same, then the multiplication would be closed or would be associative. Again, I would just remind you that multiplication doesn't really mean real number multiplication. For example, multiplication again of matrices. This would be, that's a different kind of multiplication. You have rules for this multiplication, even though we use the same symbol, which is the dot. But really, this is not the same dot as we use for real numbers. We have this one will come out to be 3. I guess they will all be 3 here, okay? Or if you change them a little bit, 1, 0, 3, 0, like that, I think you would get something more interesting. So you would get 1 and 4 over here. So you would get 0 over here. You would get 1 and a 3, so that's a 4, and a 0 and a 0, so that's a 0. Yeah, I mean, something like that, okay? So you have matrix multiplication, which follows a completely different rule. You have complex multiplication, A plus IB multiplying C plus ID. That would be AC minus BD. So the real part becomes AC and minus BD, and the imaginary part becomes AD plus BC. Okay, that's a different kind of multiplication than real number multiplication, where it would just be A dot B would be A dot B. 2 into 3, it would be 6. But 2 plus 3i and 5 plus 7i will not follow the same thing. So multiplication, again, can be very different according to the structure on which you're working, according to the set on which you're working. Okay, so to be a ring, it should follow these two properties. The multiplication should be closed and associative. R with a plus sign should be a commutative group, and those follow everything over here. And the two must be connected. The multiplication and the addition must be connected somehow. That is by what is called the distribution property. Okay, this is called the distribution property, and I'll just write it here. What it means is, if you add two numbers and you multiply, if you add two elements and you multiply an element from the left, then you can break up the brackets. In other words, that will be the same as multiplying the individual elements by A from the left and then adding them. It's like distributing the multiplication on these two numbers. Okay, that's a distribution problem. Similarly, you could do the same thing from the right. Okay, you would distribute this multiplication on both A and B. Okay, so this is called the distribution property. Right. So if these four are followed by a three tuple, a ring, a plus sign on it, and a dot on it, then it would be called a ring. Okay. This last one is an important one because it sort of connects the two. Okay, it shows how they are related to one another. The two operations. Now again, the ring can have additional properties. Again, if the multiplication is a commutative operation, in other words, you can swap the positions for all AB. In that case, if this is true for all AB in R, then this ring would be called a commutative or an abelian ring, just like before. But remember, it would be called a commutative ring if only the dot sign or the multiplication was commutative. The plus has to be commutative for it to qualify as a ring. So even if this does not hold, we can't call it a commutative ring, because by the definition of a ring, the plus sign should be commutative. We can call it a commutative ring only when the dot is commutative. Okay, you can swap the positions about this multiplication. And it can have another structure. That is, here, when we were defining what dot should be for this thing to be a ring, we did not bring in the idea of an identity, just like we did here. For groups, we had the idea of identity, and we called it the additive identity. However, if this is a ring, but it has extra structures, for example, if there is an element, which I'm writing as 1, again, remember, this 1 is not the same 1. If I'm writing an element, if I can find an element in R such that it multiplies A, multiplies by how we have defined multiplication for R. If it multiplies any A from R and gives you A, then this number or this element is called the unity. And again, I'm using a very famous or popular symbol of 1. I'm writing it as 1, but really it should not be thought of as the 1, the real number. It should not be, because for matrices, for matrix multiplication, if you have A, B, C, D, the identity, in other words, an element which would multiply this matrix, it should be another matrix, which will keep the matrix as it is, should be this element. This is the identity element. Okay, this really is the identity element for matrices, and I'm choosing to call it 1 because of uniformity. Okay, of course, this is not the same 1 as the real numbers, but I'm calling it 1 with full knowledge that I'm calling it 1 in the field of or in this on the structure of matrices. Okay. So 1 in terms of matrices would mean this matrix. Okay. So again, for complex numbers, the number 1 is not the real number 1. It is a 1 with a real part and 0 in the imaginary part. Okay. We just write it 1 because we are used to writing it as 1. But really 1 means it's not the same 1 as real numbers. Okay. So anyway, so if it has this kind of an identity element, the multiplicative identity, it would be called a unity, or I would call it the multiplicative identity if I'm calling this the additive identity. Okay. All right. So that's a group and a ring. We need one more thing to connect the group and a ring, which would be called a module, and then we will finally define what would be meant by a D operator. So let me just rub this out. So I'll rub out the heading as well because we know what we're doing now. So I'll just define what would be called an arm. So let G plus, let this be a commutative ring commutative group and R plus dot. Again, I'm using plus here and I'm plus here. The two pluses can be totally different given what the structure is on G and R, okay? So, and this be a ring. Let's say with unity. With unity, which I will write as 1, okay? So, if I have two things here, two structures, one is a group and the other is a ring with unity, then G plus will be called an R module if G and R are connected like this, okay? Number one, an element of R should act on an element of G by some kind of an action, okay? So, let's say I have an element small r from the ring and an element A from G, okay? Let's say so RA must be an element of G. In other words, we are defined. So I'm writing R and A together side by side. What does it mean? Okay, I'll just give you an example of an action. It really means that R is acting on A. So for example, if you take, so let me just give you the concrete example, okay? And we will use this example. If I take the set C infinity, what does it mean? C infinity is the set of all functions, real functions, which are derivable infinitely many times, okay? All real functions you can have complex functions as well, but let's just deal with real numbers, real functions. All real functions derivable infinitely many times. For example, you would have sine t. Sine t is a function which is derivable infinitely many times. You would have a function sine t as an element of C infinity. Exponential of t, e to the power 5t, for example, that's differentiable infinitely many times. That's an element of C infinity. Things like that. Polynomials. So this is a function. It's a set of many functions which are differentiable infinitely many times. Okay. You can have an operator like this, ddt, for example. Okay. By itself, it's an operator. It doesn't have much meaning. It's a symbol. But it may act on a function from C infinity to give you another function, which I will call f prime. That's the normal notation, really. This is an operator which acts on a function and gives you another function. So it's something like this. If you think of ddt being an element of R and f being an element of G, then R here, so this is an element, I'm calling it R, and f is the element equivalent of G, an element from G. It sort of acts on the element from G to give you an element from G, because f prime will be an element of C infinity. Because if this is differentiable infinitely many times, if you differentiate it one time, then this will also be differentiable infinitely many times. So it's like that. You think of this operator being an element of the ring, and this element being an element of the group G, then you can have action of this ring element on an element of the group to give you an element of the group. Okay, so R from the ring, A from the G, the action, I'm not putting any dot or any symbol here. It's just an action which gives you an element of G. Okay, so think about it. So if you have G and R which follow this, it should follow a few more things to be called, for G to be called an R module. So the first thing is the action of R on G should be, you can call it closed, because it takes an element of G to an element of G. Okay? It's like a function. It's like a function. If you think about it, R is acting like a function from G to G. It's taking an element A, acting on it, and turning it into a new element which I'm calling RA. Okay? It's like a function. Okay? Right. What about, and it should follow something more. If you have two elements, so if R acts on A plus B, where A and B are from G, remember, this is a group, so A plus B together will be an element of the group because of the closure property of addition. Okay? And so, because this whole thing is an element of the group, I can talk about action of an element of R on the group, on an element of the group, which is A plus B. And this should be the individual actions added together. Okay? This should happen for all R. Okay? For all R in capital R and A, B in G. Okay? If this happens, if the action is like this, that if you take any two elements from G and an element from R, and the action on this addition is sort of distributed, just like the distribution property, okay, then it goes one step towards being called an R module. Okay. Number 3, if you have R, S on A, R and S are elements of capital R, the ring, and A is an element of G. If you act on A by an element of capital R, that's an element of G, because that's what it is. Action of an element, action of a ring element on a group element gives you a group element. Now this is a group element, so I can talk about action of another ring element on this group element. If this is equal to, you put together R and S. R and S are elements of ring. So if you put together, if you multiply them by their multiplication that is defined on the ring, now this is an element of the ring because of the closure property of multiplication. And this should act on A. So this acting on A gives you, so if R, S and A, all three like this, if for any R, S and A, for all R, S and A like this, if they follow this kind of a relation, then again it goes towards being called an R module. G here can be called an R module, but it should follow the fourth one. The fourth one is that if you have R plus S, which again is an element of R, because R plus is a group, so the plus follows closure, and it acts on A, then that gets distributed. R on A plus S on A. Okay? This can happen for all R and S from ring and A from group. Okay? And finally, so this is really enough for a group to be called an R module if it is without unity. But since we are taking a ring with unity, it should follow the last one, that the unity here, so the one element, the multiplicative identity, that when it acts on any element from the group, that also has the ability to act on an element, just being an element of R, the ring. This should always give you a return the element of G. Okay, this happens for all A in G. Okay, if all of these 5 properties are followed by G and R with an action defined like this, okay, then G will be called an R module. Okay, that's so 3 things we have learned. One is a group, one is a ring, and how a group and ring can be linked together by an action. Okay, this is action of the ring on the group G. That's what is connecting them. And if this action follows all the 5 properties, then G will be called an R module. Finally, we introduce what we want to, because we want to solve differential equations. I'm introducing a ring here, and now it's up to the viewer to check that this is a ring. Okay, as I said, this is not a course in algebra, so I'm not going to go into the details of this. I've just given you the definitions. We will need these properties in the next few lectures when we talk about solving differential equations using D operator method. But so anyway, so let's come to this example. So I'm going to define a set here. This is the set of this is the real number R, okay, and this is D, capital D, which is the intermediate. This is the indeterminate, or it's a variable. Okay, we don't know what it means at the moment. So this set here contains all elements of this form: A0, A1D plus A2D square plus ... We don't know what D is. D is a variable here. Okay, and these A0, A1, they are all real numbers. That's why the real R is here. Okay, so they have a name. That's a series. It's a series of terms all added together. Okay. Now, you can imagine that. So it has a name. This name is a formal power series. An element of this kind, an element of this, which looks like this kind of a series, is called a formal power series, because it's a series of various powers of D. Okay. Now you can imagine that an element can have, so for example, if I have an element PD, which is A0 plus A1D plus A2D square, and that's it. Let's say A3, A4, A5, all other coefficients, these are the coefficients of D squared and all of them. If the coefficients are all 0 from 3 onwards, which is possible because 0 is a real number, and these numbers will have to be real numbers. If all of them are 0 from 3 onwards, then this becomes a polynomial of degree 2. That's why I've written it as PD. Okay, so really, elements in this set here are polynomials, but if they don't stop, if the coefficients are non-zero, it's almost like a polynomial of infinite degrees. Okay, that's why they're called power series. Okay, so that's what this set is made of. Okay, all elements of this kind. Now I want to define. So let's say I have P like this. Now I'm writing PD as a general, and I'm writing QD as another element from this set. B0, B1D plus B2D square. Okay. I want to define addition. Now, this is the definition of addition that I'm putting in. Okay. This is a set. Now, I'm defining addition on this set. Okay. So this addition is the new definition of an addition. It has nothing to do with real number addition. Okay. I may be using real number addition to define it, but this addition is what I'm going to define now. So if I take 2 elements of this set, I will define this addition by a term-by-term addition. In other words, A0 plus B0. This addition is a real number addition. because A0 and B0 are real numbers, plus A1 and B1, the one with D's, they are put together as the coefficient of this new element. A2 plus B2 elements of D square, they are put together as the coefficient of this new element. So this is how I have defined addition, and you can see that it is closed because these A0 and B0 are real numbers, so this will be a real number. A1, B1 are real numbers, so A1 plus B1. So this really is an element of this. So the addition is closed, okay? And in fact, you can go on to check that all other properties of addition is true for this to become a ring, actually. So let me just, I want to define a multiplication for this one as well, for this set, and this addition and this multiplication finally will turn this into a commutative ring with unity. That's what we wanted, okay? A commutative ring with unity. The way we would define it is like this. Here we will take the powers and put together the coefficients of the different powers. So for example, the one with power 0, or d to the power 0, is A0 and B0. These two will be put together. The one with d to the 1, you can get that from, so A0 B1 plus A1 B0 together with D. With D square, I want, addition of the indices should be the power of this, okay? So I'm now writing for D2, so what are the possible, coefficients? A1 B1 plus A0 B2. And I go on defining it like this, okay? Again, you can see that these are all real numbers. So this new product that I have defined is also an element of this set. So, and it's up to, and we can check this, and this is a request to the viewers that you will have to check this, that this will be a commutative ring. Commutative means this multiplication will commute, okay, with unity, which I will write 1. But what really is 1 is this series where the first element is 1 and the rest are all 0. This element, which I will write as 1, will be the unity or the multiplicative identity of this element. Okay? Right. So this will be a commutative ring. And it should also be checked that this C infinity, which is the set of all real functions and derivable infinitely many times, this with the normal addition sign, this is a commutative group. This will follow. What is the addition sign? So for example, if you take two elements from C infinity, if you take sine t, that's an element which is differentiable infinitely many times. If you take e to the power t, that's an element which is differentiable infinitely many times. If you add them, what does addition mean? It's not really the real number addition. It's a function addition of two functions. It means that if you choose a value of t and you put that value in sine t and e to the power t, whatever real numbers you get, you add that, and that will be your answer. And this you can do for all t's. So this value is really, this addition really is not a single point addition like real numbers. It's an addition. It's a continuous addition for all t's, okay? So that's the way that's the way I define addition for functions in C infinity. This will be a commutative group. In other words, it will follow all the properties of associative property, closure property, inverse property, additive identity property, all of them, okay? 0 will be the additive identity of it. And if f is a function, then minus f will be the inverse, additive inverse of it, okay? Anyway, so these are for the viewers to check that this will be a commutative group, and this set with these two additions and multiplication will become a commutative ring. And finally, I want to connect this group, commutative group, with this ring, just like I have defined a module, and you will see that this will become a module, okay? So let me just rub all of this. You know, you have gotten all the definitions of it. I want to finally define an action. I want to define an action, and this will be the end. The action of this ring on this group. I'm going to define it, and again it will be up to the viewer to check that it follows all the 5 properties, and so C infinity will become an RD module, okay? So the way I'm going to define the action is like this. Just like you can think about it, I had kind of defined it already. This was one of the actions I defined, so I'm going to define it like this. So if you take an element PD, so think about it, I have to take an element small r from the ring, and I have to define the action on an element of G, which is a function here. An element of C infinity will be a function. So let's take an element from RD, the ring, which of course looks like this. And I'm going to take an element from C infinity. It's a function, differentiable infinitely many times. I'm going to define PD action of it on F as this. Okay? So the action of A0, A1D, A2D square, the action of this PD, is just spelled out here, on F is given by the individual actions. So that is going to be A0 plus A1. What I mean by D now, that's what I will tell you. So till now I had left D out without any meaning. I just called it an indeterminate or a variable. Now I tell you what D means. D means d dt. D square means d2 dt2, and so on and so forth. So power of D really gives you how many times you have to differentiate. It's an operator, so D really is an operator, but I have so far written it as a variable, okay? So I'm now defining the action of PD on F by A0 acts on F individually as multiplication, okay? Because A0 is a real number and it can multiply a function. A1 will multiply D on F, which is the differentiation of F, one time. This is A2 down here. A2 will multiply D square on F, which is the double differentiation of F. And you go on like this. That's the action. And remember that why is this an action? Because this is an element of R, which is the ring. It's an element of C infinity. F is an element of C infinity, the group. This should be an element of C infinity. Remember, R should act on an element of G to give an element of G. So this thing, which is the action, should give you an element of C. And that is possible for some conditions when A0, A1, A2, the coefficients are bounded enough, okay? F is a good function, or sort of, defined on a closed interval, perhaps, okay? It's differentiable and infinitely many times. So it has to be, it has to have certain properties, and we're not going to go very deep into what properties it can have. That's into analysis. But for the moment, we just say that if you add all of this up, it gives you a good function, which is, again, differentiable infinitely many times, okay? So that's the action. This is how I've defined the action. Please check that it follows all the 5 properties. And so C infinity is an RD module. Technically, it would be called a left module because R is acting on F from the left. The elements of R are acting on F, or elements of C infinity from the left. But we'll just let go of that. This is the important thing, the important conclusion from this lecture, and we will continue with this. We will build up. This is what the theory of from algebra, from rings and modules that we need. As I said, this lecture really is a digression from all that we have been doing. We have only talked about algebra, except towards the end we have defined what would be differentiations and second order differentiations like that, and we've defined them again in terms of ring action on a group, and we have saying that this would be a module. So all that we have done in this lecture is just pure algebra. But I hope in the next lecture we will be able to turn things around and use the properties of all that we have written down today, okay, and use them properly to actually solve differential equations, second order linear differential equations with certain kinds of inputs, okay. Inputs which will have to be from C infinity. All right, so we will finish this here, take things forward in the next lecture. Thank you.